energy theorem. It is significant and it has a mathematical form, and it uses the third equation of motion, which is 2s equal to v square minus u square, and from here we take the value of a as v square minus u square by 2a 2s, sorry, the distance, final velocity square minus initial velocity square by 2 times the distance covered. And we also know that work done is equal to force dot distance, and we assume that both are parallel, so theta is equal to 0 degrees, which makes cos 0 to be 1. So we substitute f with ma and put dot s, and now we take the value of a and put it in this equation. Yes, so ms dot a be equal to ms dot v square minus u square by 2s. S will cancel out, so mv square by 2 minus mv square mu square by 2, as which means what? Which means work is equal to kinetic energy final minus kinetic energy initial. Yes, because v is the final velocity and u is the initial velocity, and kinetic energy is equal to half mv square. So this is a form for work energy theorem. Now we have this simple pendulum. And simple pendulum is interesting. Simple pendulum. Okay, so the free body diagram would be like this. Theta, length L of the cord, angle theta it makes in the body as it is suspended, and it has now components of force. Yes, so this one is x component of weight, and this one is the y component of weight. Yes, So x component is mg cos of theta, and y component is mg sine of theta. Yes, so this is to begin with, and since in this case if we exaggerate, theta is very small and roughly equal to 0, so sine theta can be approximated to theta. And as we know that x is equal to r theta, where x is the displacement from the initial position, the center to the side, and it makes an arc, and this is equal to L theta, the radius of the circular motion, and angle theta. So theta would be x by L. Okay, and since I pointed out that the force responsible for the simple simple pendulum is the vertical component of force, which is um, very much mg sine theta, because of the direction, is equal to minus m, is equal to minus f is equal to minus mg theta, and theta is equal to x by L here. So we use this first substitution, and put it here. F is equal to minus mg x by L. So this is a form we have. Okay, but now at the same time, this is equal to, in a mass spring system, or a mass attached to a spring and an oscillatory or to and fro motion, F is equal to kx, negative kx rather. Yes, so now we can equate negative kx is equal to minus mgx by L. Minus cancels out and x cancels out, so what we are left with is k is equal to mg by L. Yes, mass into acceleration due to gravity by the length of the pendulum is equal to the spring constant k, or the constant of proportionality, in other words, uh, the ideal situation, but here it is rather related to the simple pendulum and the tension of the cord. Yes, and so we will look further into the pendulum later. So we have further topics. Momentum. So we have to develop form for momentum. As we know that Linear momentum is directly proportional to the mass, and linear momentum is also directly proportional to the velocity. So here's the mass, and here is its velocity. Yes, mass m. Excuse me, mass m, and it has the direction of motion, which gives it the velocity.